All right, everyone. Good morning. Welcome to our Business Mathematics Masterclass. Today, we're going to tackle a concept that I know might look a little abstract at first glance. It's called LU decomposition. But I promise you, by the end of our session, you'll see it for what it really is, one of the most powerful, practical tools in all of modern business analysis. This isn't just about theory for an exam. This is about giving you a real-world edge, the ability to make faster, smarter, and more strategic decisions when you're faced with incredibly complex problems.
So here's our roadmap for today. First, we'll set the stage, talking about the kinds of massive business puzzles that even require a tool like this. Then we'll dive deep into LU decomposition itself, what it is and how it works. We're going to walk through the actual mechanics step by step. And then, the most important part, we'll connect the dots from the classroom to the real world with some powerful business applications. We'll also cover the common mistakes people make so you can avoid them. And we'll wrap up with the big strategic lesson I want you to take with you into your careers. Okay, so first things first, let's get the context right. The world of business today isn't about solving one simple problem at a time. It's about managing these huge, interconnected systems. Think of it like a giant spider web. You pull on one thread over here, and the whole web trembles. In mathematics, we call these systems of simultaneous equations, and they are everywhere.
I mean, really think about this question. How does a company do this? Put yourself in the shoes of a logistics manager for a global shipping company. You have thousands of packages, thousands of destinations, and a fleet of trucks. You need to figure out the absolute best route for every single truck, right now, to save on fuel and time. And guess what? A traffic jam happens in one city. That one variable changes, and now you have to recalculate everything instantly. Or think about an airline. They're setting prices for hundreds of flights. The price depends on fuel cost, what their competitors are doing, the season, even the day of the week. It's a massive puzzle with thousands of moving pieces, and they need a solution now, not next week. This is the kind of high-stakes problem we're here to talk about.
And that brings us right to our star player for today, LU decomposition. You can think of it as this incredibly elegant and efficient engine that allows us to take those massive tangled puzzles and solve them with surprising ease.
So, what is it, really? Well, at its heart, LU decomposition is a way of breaking things down. It's a form of matrix factorization. We start with our big, complicated problem, which is represented by a single matrix we call A. And the whole idea is to split that one complex matrix into two much simpler ones. A matrix L, which stands for lower triangular, and a matrix U for upper triangular. Now, all lower triangular means is that all the numbers are on or below the main diagonal line of the matrix. Everything above it is just 0. And upper triangular is the exact opposite. All the numbers are on or above the diagonal.
This slide really shows you what's going on visually. Look at the left. That's matrix A. It can be dense, filled with numbers everywhere. It looks complicated because it is complicated. Now look to the right. See the L and U matrices? Notice all those zeros? That's the secret sauce. That clean, simple triangular structure is what makes them so easy to work with. Solving a system of equations with a triangular matrix is incredibly fast. We use a simple process called substitution. So, by breaking A into L and U, we've basically turned one very hard problem into two relatively easy ones. And this right here, this is the golden rule. A equals L times U. This is the goal of the whole process. We need to find the one specific L and U pair that when you multiply them back together gives you your original matrix A perfectly. It's so important to get this. We're not losing any information here. We're just rearranging it. We're repackaging it into a format that's way more useful and computationally efficient.
Okay, theory's great, but let's actually see how this is done. It's time to roll up our sleeves. We're going to walk through this together step by step, just like a hands-on workshop.
We're going to use this simple 2x2 matrix from our source material. This way, we can see all the moving parts without getting lost in a huge grid of numbers. So, our matrix A has a top row of 4 and 3 and a bottom row of 6 and 3. Our mission? Find its L and U matrices. Our first job is to find the U matrix. And we do this using a process you may have heard of called Gaussian elimination. The only goal here is to get zeros in all the spots below the main diagonal. In our little 2x2 example, we just have one spot to worry about. That's 6 in the bottom left corner. We need to turn it into a 0. So how do we do that? We need a multiplier. To find the multiplier, you take the number you want to get rid of, in this case 6, and you divide it by the pivot element, which is the number above it in the same column, the 4. So 6 divided by 4 gives us 1.5. That's our magic number. Now we take that 1.5, multiply it by the entire first row, and subtract that result from the second row. Let's do it. 1.5 times 4 is 6, and 1.5 times 3 is 4.5. So our new second row will be 6 minus 6 and 3 minus 4.5. That simplifies to 0 and negative 1.5. The first row doesn't change, so our final U matrix is 4, 3, 0, negative 1.5. And there you have it, an upper triangular matrix U.
So you're probably thinking, okay, that's U, but where does L come from? Do we have to do a whole other set of calculations? And the answer is no. This is the most elegant part of the whole process. We actually built the L matrix while we were making the U matrix. Here's how it works. The L matrix always has ones on its main diagonal. That's a rule. And the other numbers, they're simply the multipliers we just calculated. Remember that 1.5 we used to get the 0? We just take that number and we plug it into the exact same spot in the L matrix. Second row, first column. So our L matrix is 1, 0, 1.5, 1. And just like that, we're done. We've successfully broken down A into L and U.
Okay, we've done the math. Now for the million-dollar question, right? Why on earth did we just do all of that? Why does any of this matter to you as a future business leader? This is where we bridge that gap from the classroom to the boardroom. Because this process, this is a cornerstone of modern quantitative analysis in business.
As our source material points out, this is not some obscure tool that only exists in textbooks. This is the workhorse running under the hood in a huge range of fields. We're talking sophisticated financial modeling, optimizing global supply chains, engineering simulations, pretty much any field where you have to solve the same type of complex system over and over again, very, very quickly. You can bet LU decomposition is working behind the scenes.
So let's run with that finance example. Imagine you're the CFO of a major investment firm. You have a massive, complex model that analyzes market risk. The core structure of that model, the relationships between thousands of different stocks, bonds, and economic indicators, that's your matrix A. That structure doesn't change much day to day. But what does change every single second is the input data, the latest stock prices, interest rate changes, news headlines. You need to rerun your risk analysis with this new data constantly, maybe every hour or even every minute, to make smart investment decisions.
And this slide, right here, this is the big payoff. This shows the massive strategic advantage you get. The brute force method, on the left, would be to resolve the entire complex matrix A from scratch every single time new data comes in. That's slow, and it's incredibly expensive in terms of computing power. But look at the right. With LU decomposition, you do the heavy lifting one time. You decompose A into L and U. And from then on, every time new data comes in, solving the system is ridiculously fast. It's just a simple two-step process of substitution. You're making a one-time investment in computation that pays you back over and over again with incredible speed and efficiency.
Now, like any powerful tool, you have to use it correctly. I have seen so many students who understand the concept perfectly, but then stumble when it comes to actually doing it. So let's talk about the common traps people fall into so you can sidestep them. Honestly, the biggest mistakes I see are almost always in the small details, not the big concept. A simple arithmetic error, a plus sign that should have been a minus during the row operations, can throw your entire U matrix off. But the number one mistake, far and away, is messing up the L matrix. People forget to put the ones on the diagonal, or they put the multiplier in the wrong spot. You absolutely have to remember, the multiplier you use to create a 0 in, say, row 3, column 1 of U, that exact multiplier goes into row 3, column 1 of L. So my advice is simple. Be neat, be systematic, write everything down, and double-check your work.
Okay, so as we start to wrap up, let's zoom out. Let's synthesize all of this. What's the big strategic takeaway I want you to walk out of here with today?
The most important thing to understand is that LU decomposition isn't just another formula to memorize for a test. It's a way of thinking. It's a strategic approach to problem solving. Knowing this method is really about knowing how to take a big, messy, complicated problem and structure it in a way that makes it efficient to solve. Not just once, but over and over again, at scale. It's about building speed right into the DNA of your analytical model. And so I want to leave you with this final question to think about. What we've discussed today is about seeing a business challenge and recognizing that it can be modeled, decoded, and solved efficiently. LU decomposition is one key that unlocks a certain type of problem. As you go forward in your careers, I want you to constantly be asking yourselves, what's the right key for this problem? Because finding that key, finding the right mathematical approach to unlock the next big, seemingly impossible challenge, that is the mindset that will set you apart and allow you to create some real lasting value in the world.